I'm going to speak to you a bit about urban heat and its relation to trees and public health. And I'm actually from South Africa, and when I arrived in Oslo in January this year, I was cold. It was very cold. And it was very surprising, and my colleague David Barton said that I'm going to be working on or studying the urban heat island effect. It was very surprising given the current conditions at the time. But Oslo does get hot in summer. It gets up into the mid-30s, and there's an estimate to say that Oslo will increase by 5.6 degrees by 2050, and that's similar to the climate of Bratislava, which is in red here. So it's much warmer, much further, similar to an analog city that's much further down south. And this is important in cities because in cities, due to the urban heat island effect, climate change global warming is maximized and it's experienced in more extremes. And the urban heat island effect is where urban surfaces trap heat, absorb heat, and retain it within the urban canopy. And you can see this by the image on the right, which is a thermal infrared image of a street canyon showing hotter temperatures just above the street surface and within the building canopy. So why is this important? Why is urban heat important? Why should we care about it? Well, mitigating urban heat is essentially important to reduce human mortality. And I was very surprised to find out that heat is actually the most lethal climate-related disaster in the world. And it's a silent killer because not many people know about it. But for example, the heat wave in 2003 in Europe led to 35,000 deaths, which is amazing for me, coming from a country like South Africa, where I guess we are more used to heat. But this graph shows in red the temperature over Paris during August, and you can see that the spike in temperature is shortly preceded by a spike in mortality in yellow. And so mitigating heat is quite important to reduce heat-associated illness and mortality. And in a city like Oslo, although we don't experience as extreme temperatures as a city like Paris, this might change in the future. So what can we do about it? Well, green infrastructure is one of the main ways of mitigating urban heat. And this map shows the percentage green area within 250 meters of every building in the city. And the height of the bars in this image indicate the density of the people living in that building. And it's interesting that the areas in red, which have a deficit in green infrastructure, actually coincide with the areas that have the highest population density. So there's actually a high demand for green infrastructure in areas in Oslo. And what we wanted to try to do is quantify the contribution that trees make to reducing heat risk in Oslo, and maybe help urban planners know where to plant trees and where not to cut trees down. So what we did was use an ecosystem accounting framework, and this is known as the Ecosystem Cascade. First, we defined the ecosystem structure. What is the land cover in Oslo, and particularly what is the percentage tree cover? And then we relate this to the ecosystem function, and this, in this case, is the reduction in surface temperature. And we used a counterfactual modeling scenario where we sort of imagined or modeled a doomsday Oslo where all trees were removed. How much would that increase the temperature? And then we relate this to the ecosystem service, and we use this statistic called heat risk person days. And this is essentially the number of days in the year exceeding 30 degrees Celsius multiplied by the number of citizens above 75 years old. And we use these thresholds from the UK Heatwave Action Plan because at the moment Oslo and Norway in general don't have such heatwave plans. But these thresholds can obviously be adjusted in the future. So we went out and we measured using satellites the surface temperature over Oslo. In the image on the left, you can see that the center of Oslo is the hottest, and as you move out into the Marka, the temperature cools down. And when you measure this per landscape element on the left-hand axis of this graph, And on the right-hand side is the temperature on the right axis, and that's indicated with the black line. As you move from landscape elements that are dominated by trees to those that are dominated by paved and building surfaces, there's a 10 degrees increase in surface temperature. So using this empirical relationship between tree cover and temperature, we then carried out the counterfactual doomsday model, where what would Oslo look like in terms of surface temperature if we cut down all of the trees. And this map shows that, and you can see that in the urban periphery, in the suburbs, there's up to a 3 degrees increase in surface temperature if we had to remove all of the trees in those suburbs. Another way of looking at this is to look at the surface area of Oslo that exceeds 30 degrees Celsius during the summer months. And that's on the y-axis of this graph on your right. And you can see that, so it's in weekly time intervals over the summer. And in a city without trees, you bump up the surface area by, on average, about 20% through the summer. So in Oslo without trees will be warmer. And then how do we relate this to the heat risk exposure for elderly citizens? The next thing was to quantify this ecosystem service using the statistic heat risk person days. And this map shows the distribution of the change in heat risk person days. And I'll put this animation on the left to illustrate the chloropleth, or this color scale of this map, which goes from blue to yellow. Yellow being, for every single tree removed in Oslo, there are up to 3 additional people that are exposed to high risk of heat exposure. And you can see some of the suburbs in yellow over Oslo are presumably where there's a higher density of elderly people and currently a high density of trees, so that if you remove trees, you drastically increase the risk of heat exposure. And if you average this number across the whole of Oslo, it equates to about an increase of 1.32 heat risk person days per tree removed. And if you round this down to 1, it tells quite a nice story that removing 1 tree increases the heat risk for 1 person by 1 day. This is quite a nice way to account for the contribution of trees to potentially reducing heat risk exposure in the city. But it's not all. There's still more we can do. And I've just put this here to show some of the next steps are really, a lot of them are methodological. We'd like to get more real estimates of air temperature, which is more relevant to human health than satellite measures of surface temperature. And also gives you the high temporal frequency. How does heat risk change through the day in different parts of the city? And this animation is an interpolated surface using private weather station data in Oslo. Those are the white dots in the animation. And there are currently, I actually just worked it out the other day, that there are 12,000 of these stations scattered across urban areas in Norway. And you can see this hourly time interval time lapse over the hottest day during 2018. And we can use this to quantify the spatial relationship between air temperature and public health statistics. We can also use this to forecast risk under climate change scenarios. We can also assess the diurnal patterns in heat riskscape. Temperatures at night are actually have been known to be as significant as temperatures in the day in terms of heat-related illness. And we can also then link this to financial accounting of trees' contribution to mitigating heat risk. How much does 1 tree reduce Oslo's public health bill every year? Thank you very much.